Welcome to our discussion on getting information from graphs. Basically, being able to read a graph, either using technology or by hand, is a very important skill you're going to need for a lot of disciplines and a lot of possible, sources of employment. So it's a good idea to know how to look at a graph and figure out what's going on. So here are the objectives for this video, right? We're going to figure out domain and range. We're going to compare values, be able to solve things graphically, figure out where functions increase and decrease, and then also locate maximum and minimum values because those are always important. We always want to know when things max out and when there are minimums. Think about maximizing revenue and minimizing cost. So just some words on why this is important. All right, so let's start with domain and range. We all know what the domain and range of a function are, hopefully at this point. The domain is everything we're allowed to plug into the function. Remember, we only have two things that restrict our domain. We can't divide by 0 and we can't take even roots of negative numbers. Other than that, we plug anything into our functions. And then the range just describes the maximum and minimum heights, right? How high up and how low down does our function go? And the range is everything in between those two values. So here's a typical example. If we have temperature, a temperature function where it's temperature between noon and 6 p.m., where noon is considered 0, right? And then, so it's hours past noon. So 6 p.m. is just 6 hours past noon. And we can see from the graph that it reached its maximum at 2 p.m. That's one thing we could figure out from it. And if we look more closely, we can see that that maximum looks like about 34. We can also look at the graph and say that temperature was increasing, right, from noon to 2, and then decreasing from 2 till 6. And actually, it looks like it started to level off, but it was still just decreasing a little bit. And then later on, we'll be able to talk about what it means to be concave up and concave down. All right, so from the graph, we can do all these things. We can find values at certain points. We can compare values. We can find times for which the function is above a certain point or equal to a certain point or below a certain point. We can find net change. We can find average rate of change. Right? We can find all these things just from looking at the graph. And of course, they're going to be approximations because we're, pulling numbers off of a graph and we might not be totally accurate because, you know, sure, 1 o'clock looks like it's pretty darn perfectly at 25, but it also looks like it's maybe a little bit above 25. So the downside to using graphs is you don't often get really super accurate numbers. Okay, so T1, right, the height of the graph at 1, so thus T1 is 25, like we said, and it looked like it might have been a little bit above it, but we're just going to go with 25. And then if we look at T3 and T5, we can see at 3 o'clock it hit right there at 30, and at 5 o'clock it hit right there at 20. And it was awfully nice of them to give us examples that hit right on the cross marks. But that's not always the case, and it doesn't have to be, right? We could still say that T2 was 34. All right, since the graph is higher at 2 than at 4, it follows that T2 is larger than T4. That was our second question, right? Which one was larger? We wanted to find the value for which the function, right, t of x equals 25. They're basically saying, when was it 25 degrees? And you can see that it hits right here. Sorry, that's 20. 25 hits right here at 1. And if we follow it across, it also hits right here at 4. All right, 1 and 4. And the last thing, or the next thing, when was it greater than or equal to 25? So again, if we kind of draw a line on our graph at 25, so we have a cutoff, here's 25. We're basically asking, when is the function above it, right? When is it up here in this area? And we can see that it happens from here to here, which means it happens from here to here, or from 1 to 4. Right? These are pretty simple questions. They can get more difficult. All right, the last question they had was, what's the net change in temperature from 1 to 3? Right? They want to know going from 1 to 3 right here. Well, if you look at the graph, at 1, we have 25. At 3, we're up here at 30. Right? And so net change is basically just change in y's. So 30 minus 25 is 5. And if we want to do average rate of change, remember that average rate of change just equals f of b minus f of a, the change in your y's, over b minus a, right? It basically is change in y over change in x, which is just slope. We already found change in y, and then change in x, you're going from 1 to 3, right? So if we're doing 30 minus 25, we do 3 minus 1, and we get 5 over 2, and that's going to be our average rate of change. It was basically, increasing, because it's a positive number, by 5/2 or 2.5. So it's like 2.5, and then what are our units of measure? It's degrees, right? Degrees Fahrenheit per, and our units were hours, right? So it's going up by 2.5 degrees per hour. All right, domain and range, we know what those are, right? It's the x values and the y values, and we can figure those out very easily from graphs. We just have to assume that when we see graphs that go off the edge of the screen, that whatever they're doing when they get to the edge of the screen, we have to assume they keep doing that. So if we have something that goes off on the right in an upper direction, we have to assume that it continues to grow, that it doesn't get to some point and then just stops or turns around and comes back down, right? So that's one of the downsides of doing it from graphs, is we have to make some assumptions about what happens on the endpoints. So we can use a graphing calculator to draw the graph of the square root of 4 minus x squared, and then find the domain and range. If you graph it, it's going to look basically like the upper half of a circle. And then you can see very clearly that the domain goes from -2 to 2. And if you zoom in, you can see the top of that circle hits up there at 0, 2. So we know the range goes from 0 to 2. And they're all square brackets because all of those points are included. All right, what about comparing values, being able to solve things graphically? Well, later on, we're going to learn how to graph just one inequality and shade graphs to figure out what's going on. In some of these examples, we're just kind of comparing. So when we talk about inequalities, it's more about comparing one function to another. So if you look at this, we've got two functions, the f and the g function, where right now you can see the g function is the one on top, and the f function is this one down below. And if we're trying to kind of solve things like, when do the two functions equal each other? Well, we can see very clearly where they intersect, and we have those 2 points, A and B, and on the graph we would have to zoom in and figure out roughly what those points are. We could also figure out when one graph is less than the other, right? It's very obvious where f is less than g, and it's in between A and B. And then if we want to know when g was less than f, we can see that g now dips down and goes below f here and below f on the left, so it would be everything above b and everything below a, assuming, right, that these functions continue in their trajectories, because the graphs have stopped, right? So we're not really sure. Okay, so if we wanted to solve any of these things graphically, we could just graph the two pieces, right? The piece on the left is a quadratic, the piece on the right is a line, and then if we want to know where they're equal and less than or equal to, et cetera, then it's just a matter of looking at their graphs. So here's the graph of the two functions. The quadratic piece, right, the piece that was on the left, the 2x squared plus 3, the straight line piece, the 5x plus 6, and then we can see where they equal. Well, they hit at those 2 points, you would have to zoom in and figure out where they are in the graph, and they end up being -1/2 and 3. Now, it's kind of a silly exercise, to be quite honest, because if you were really trying to solve any of these, any of the 3 that we saw on the previous slide, and I'll put back just the first one, which was 2x squared plus 3 is equal to 5x plus 6. Why would you go to the hassle of graphing these things and then trying to zoom in and find solutions which you might not find perfect? These were nice. They hit at -1/2 and 3. But what if they weren't and you had to like approximate where they were? Why would you do that when instead all you have to do is solve it algebraically, right? Move all of this stuff over because you see that this is a quadratic and you have to set quadratics equal to 0. And you've got 2x squared minus 5x, right? When you move this over, you subtract the 6, so you're left with -3 equals 0. And then you just do some factoring. It's got to be 2x and x. The if it's factors, these numbers have to be 3 and 1. And since you need a 5, you could have a 3 and a 1, which give you 3 and 2. But they would both have to be negative, right? And that wouldn't work here because one has to be negative and one has to be positive. So it's got to be -3 and +1, because that'll give you -6 plus 1, which is -5. You set each of these equal to 0, and here's your answer of 3, and here's your answer of -1/2. Much better than doing it graphically. And even if it's an inequality, right, there's really no difference to a less than or equal to, because we've seen the technique that if this was now a less than or equal to, all that we do is we now take these two numbers that we found, we plot them on the number line. We don't have to be accurate, just put them where they are. One's going to be to the left of the other type of thing. And then now we're just checking to see which of these 3 quadrants, right, parts of the number line, satisfy the inequality. So you pick a number, and I always pick 0 first because that's the easiest one. And 0 is in this quadrant here. So if I plug 0 into each of these 2 factors, I plug 0 here, I get 1. I plug 0 here, I get -3. 1 times -3 is -3. That is, in fact, less than 0. So that that section works. I try something to the left of -1, or sorry, -1/2, so I try -1, and -1 would give me -2, right, plus 1, that's -1. This is negative. Negative times negative is positive, so that fails. Something bigger than 3, like 4. 4 makes this positive. 4 makes this positive. Positive times positive, right? So it fails there. So the only place where this thing is less than or equal to 0 is in between these two numbers. And because it's a less than or equal to, we go, okay, it's from -1/2 to 3 with square brackets. And we can see here from the picture that that is, in fact, because remember originally we were up here at this one, that is, in fact, where the parabola is less than the straight line. But we don't need to do that graphically. We can do it the other way. And then the third example, instead of a less than or equal to, it was a greater than. So if we change this and made it a greater than, well, we just figured out that these were the 2 spots where it wasn't less than or equal to. So those are the 2 spots where it's greater than. And because it's a strictly greater than, right, not a greater than or equal to, it would be -infinity up to -1/2 with a round bracket, and then union 3 to infinity. Much easier and simpler than having to do the graph and look at the graph and go, yeah, it's above here and here, so it's all of this and all of this, right? So it's nice to know that we can get these things from graphs, but it's much better and simpler and more precise to do it algebraically. So here are the 2 examples that we just saw algebraically. Here they are graphically. All right, what about increasing and decreasing? There are techniques for figuring out when it increases and decreases algebraically, something that you're not going to learn in this class. So you're going to have to rely on doing it from a graph. And doing it from a graph is very easy, right? We all know when it's increasing and when it's decreasing. So we can look at this function and very plainly see that it increases from A to B, decreases from B to C, increases again from C to D. Very, very simple. And we could also figure out when it's concave up and concave down, but again, uh, those things will come later. You'll notice that the increasing and decreasing stuff changes at minimums and maximums, right? We can all notice that B is a max and C is a min. So again, these things tie together. We're trying to find maxes and mins and when it's increasing and decreasing, and they're related. All right, so definition of increasing, I don't think we need to waste our time here. It's kind of a no-duh thing. We know when things are increasing, we know when things are decreasing, but here it is in specific math speak. Okay, so here's another example where we can sketch a graph, find its domain, and find the intervals where it increases and decreases. So here's the graph, and then we go, all right, well, the domain. Well, if I assume that this keeps going down and to the left, then it's going to get as low and to the far left as it can. And if this keeps going down and to the right, then it, again, is going to go as low and as far to the right as it can happen. So to me, it looks like the domain is everything. And of course it is, because we'll learn later that anytime we have a polynomial function, right, a function that's just a bunch of different powers of x added and subtracted together, that domain is always all real numbers. Because remember, the only two things that restrict our domain is dividing by 0 and taking even roots of negative numbers, and polynomials never have either of those by definition. So we're allowed to plug everything into it. The domain is everything. Now the range, we can quite clearly see that the maximum value hits right here at the top of this little hump here. And if we come across here, it's, oh, I don't know, maybe a little bit higher than the third tick. And well, if this is supposed to be 40, then these must be 10 each. So it's a little bit bigger than 30, maybe 31, something like that. And then the minimum, well, if we assume these keep going, the minimum is going to be all the way down at negative infinity. So if we put that all together, and if we wanted to be more accurate, we could use the trace feature on our calculator. And when we get up to that maximum, our calculators also, by the way, have a maximum and a minimum function. And you could just use the maximum function and it'll find that maximum value for you. And so my estimate of 31 was a little off. It was actually 32. And it happened right there when x equals 2. And then, so that tells us the range, right? Negative infinity up to 32. Now, from the graph, we could tell when it was increasing and when it was decreasing, again, by just looking that it's increasing up to about there. So if this is 2.5, right, 1, 2, 3, 4, 5, then this is a half, this is 1. So it increases up from negative infinity to 1, decreases from negative 1 to 0, increases from 0 up to 2, and then decreases from 2 down to infinity. Simple, easy stuff we can get from the graph. And also we can use the trace function and other things in our calculators to get those points more accurately. All right, minimum and maximums, we know what they are, right? There's a couple local maximums, a couple local minimums. We can find them by just looking at the graph. We can also use calculators to get a better answer than just looking at the graph. So if we were looking at this, we'd go, okay, the maximum is somewhere in between these two marks, somewhere in between those two marks. But if you want to put it into a calculator and graph it, then you can use the trace function and you can move and, oh, hey, that looks like that's about the maximum right there, right? But you can also, instead of using the trace function, you can do second calculate and find a maximum. It asks for the left bound, so I can see right now that that's to the left of where my maximum is, so I'm going to hit enter, and then it wants to know where the right bound is, so I just have to move the cursor to the other side, anywhere to the other side of the maximum, hit enter. It always asks for a guess. You don't really have to do this, but I like to put it kind of close to where I think it is, and then it calculates it, and there it is. A maximum when x equals negative 1.633, and the maximum value is 9.71. Okay, And then we could do the same thing for this minimum. And as we can see, right, from looking at the graph, we know it's between -2 and -1. And to remind ourselves, it was -1.6, right? And if we use that trace function, we can get close to it. Here's what they found, right? -1.633, which is what we got from our function. They probably cheated and used the same function and just pretended that they used trace. All right, and then we could repeat the process for the minimum and get the minimum values there. All right, so that's pretty much everything that we're going to do with finding information from graphs.